At the first virtual Ifac World Congress, all plenaries and semi-plenaries are accompanied by an entertaining live element. This presentation is followed by a live demonstration presented by the speaker.
Welcome now at the lab of Professor Albuschefer in Munich at the German Aerospace Center. As usual, we have a live event after the plenary lecture. The previous plenaries had very interesting live panel discussions, and we will have one as well, but in very different setting. Today, we will join with robots as panelists. A live panel with robots is most exciting, right? And I'm already curious about the topics of our discussion. Alin, what you and your panelists have prepared for us?
Oh, hello everyone, and welcome here at the German Aerospace Center. We prepared 3 different demonstrations, and we will start here in the healthcare lab. You have seen some of the videos, and I would like to introduce Jörn Vogel. Jörn, tell us something about your experiments.
Yes, welcome everybody to the healthcare lab. We will show you today some elements of the ecosystem that you have already seen in the plenary, which we intend to use for assistive robotics in care scenarios. And the first demonstration will be Eden, our robotic wheelchair, which is a commercial wheelchair equipped with an 8 degree of freedom robotic arm and hand, in which we've implemented various features of Cartesian impedance control, whole body control, and shared autonomy.
So you are showing here very advanced tasks for service robotics, far beyond cleaning floors. Here the robots is operating and acting closely with humans. So what makes a robot capable collaborating safely with human, in particular when having disabled partner as in our case here?
So our robot is torque controlled, so we have true Cartesian impedance control.
So Jörn, what kind of tasks do you offer to Gabriel?
A drawer, or picking this bottle and pouring a drink, and afterwards grabbing the mug and drink from it. And the user is free to choose.
Okay, giving him a drink is a good choice. What about a gin tonic?
Yeah, let's see. I mean, Gabriel can basically come over and fetch himself a drink, and we can see how this works.
So I'm most amazed about your robots because they are very skillful and interacting with their environment, performing real mechanical tasks. And it is well known that your robots are integrating mechatronics and robotics in a very unique way. So where is the border of mechatronics and robotics in your machines?
So we really care for having a fully integrated system, and basically I would say the border vanishes because we are combining the mechatronic skills with AI and other robotic disciplines to achieve this capability of the system.
So the most interesting thing here is that robotics combines all engineering and computer science disciplines, right? Mechatronics is the basics, then on top advanced control, and then AI for perception and planning. But more and more also medical sciences, psychology, and so on. So we put it all together to get advanced robotics.
So while Gabriel has been pouring his drink, also our second system of the ecosystem, Justin, has prepared. He has autonomously opened a drawer and picked up an injector from the drawer. And now we will show some teleoperation features, which our teleoperator using the haptic user device will show now. So as you can see on the left of the screen, the teleoperator is using two robot arms as control inputs, and he's now currently using them as joysticks to drive the platform, but he can also use them to operate the arm.
So basically what you see here is Michael diving into the robotic avatar. So he sees through the eyes of the robot, commands the positions, but also when the robot is interacting with a human, he will feel the interaction forces. And maybe you can say also about the experiments at long distance we performed. Of course, here the colleague is in the neighbor room.
Yes, so we have also used this in the experiments run from the ISS. So basically we had a joystick on the ISS to operate the robot here in the lab. And we've also done this over the internet from St. Petersburg.
So now we are going to space, right? Space robots.
Yes, we will. Yes, we will also show a space application now.
Indeed, we are here at the second experiment. So now we are in space and looking at some space robotics experiments. And I would like to introduce Roberto Rampariello. Roberto, say us a few words about this system.
So thank you, Aline, for the introduction. Welcome to the OSSIM. The OSSIM facility, which you can see here on my right, we use it to simulate on-orbit servicing scenarios. There are two main players on the facility that you can see now on the image. On the left-hand side, we have a chaser robot, and on the right-hand side, we have a target robot. The target robot is meant to play the role of a defective satellite in Earth orbit, which needs to be captured and eventually repaired. On the right-hand side, the chaser carries a robotic arm. We have here a lightweight robot, the orange robot that you can see in the image, which carries a gripper and a stereo camera. So the two industrial robots are necessary to move the two satellites such that we can simulate the weightlessness in space.
So, Roberto, what makes space robotics like this servicing task so difficult to verify and validate on ground?
So basically, yes, we need on ground to reproduce the weightlessness that we have in space and also the harsh light conditions that we have. And this is exactly what we do with this facility. So I want to show you our first demonstration out of 3, in which we concentrate on the system on the left, basically the chaser plus robot arm. And this is fully actuated, fully controlled. We have the chaser position and attitude being controlled, regulated about a point. And also the end effector of the robot arm equally being regulated about a position and attitude. So my colleague behind me has a little cable in his hands with which he can apply an external force to the end effector of the robot, which the robot is actually holding on to with its gripper. So he will pull the cable twice. He will do that once now. And we can see 2 things. The first is that the force is being reflected on the whole system, which then drifts down. The second one is that the controller then recovers the error and brings the system back to its equilibrium point. So we will now show it again. You can then concentrate on the motion of the robotic arm, the orange lightweight robot, which behaves like a damped spring, which is the feature of the impedance control that it can perform because it's torque controlled.
So with your left robot, you are simulating, mimicking the attitude control system of the satellite, right?
Absolutely, yes. So we are assuming that the chaser has thrusters active. So now in the second simulation, actually, we switch off these thrusters. So the chaser robot is not actuated, it's not controlled. We have let go of the cable that was attached at the end effector of the robot, such that we can now simulate the next dynamics, which we call free floating, in which there are no external forces acting on the system. And to demonstrate this dynamics, we command a reference trajectory to the robotic arm. And when doing that, you will see dynamic coupling, which takes place between the motion of the arm and the motion of the chaser underneath it, which is governed by the conservation of momentum of the system with absence of external forces, as we said, and which presents special difficulties when wanting to control the arm, for example, to reach out and grasp the target satellite, as we will do next. So now it's performing a closed loop maneuver, which is also an interesting detail of this kind of dynamics. It's a non-holonomic dynamic system, after which, by performing closed loops of the robot, we can achieve rotation, so changes in attitude of the chaser satellite. So now we move on to the next demonstration, the last demonstration, which is the most challenging. It's the grasping of a tumbling target satellite. It is challenging because we have contact, and this is what this facility is also about. It's about physical contact. We don't simulate the contact, but we really measure it with sensors in the facility. And the lightweight robot will then establish contact and close its gripper on the target while it's tumbling. And this is only possible thanks to the fact that we have the compliant behavior of the lightweight robot, which closes the loop between the two position-controlled industrial robots. This compliance behavior is also useful in space to avoid effects.
Roberto, it's interesting. It's interesting. So compared to terrestrial applications, there are very few robots in space so far. What makes it so difficult putting robots to space?
Yeah, so the harsh environment. So basically, we have a lot of radiation up there. We have a lot of thermal gradients and things of the kind. So we now will start the spinning of the satellite, and we can then home in with the lightweight robot as soon as the grasping point is in reach. And you will see how the LBR then, yes, so now it is guided by a visual tracker onto the grasping point, and it will now close the gripper onto the grasping point, and as such, we now have closure. And the system now tumbles on freely, conserving the angular momentum of the system. You can see the closed kinematic chain with 19 degrees of freedom, and the system is stable because of an energy observer that we implement in the simulation of this hardware in the loop simulation. Well, thank you very much.
Okay, so we are now at our third location, and this is the LEGT Robotic Lab. Here we have two robots waiting for us, and the first one is the humanoid Toro, and Christian Ott is the one presenting this humanoid system.
Okay, so we will show today some locomotion behaviors for our humanoid robot Toro, which has 6 degrees of freedom in each of the two legs and in the arms. And the control algorithms which we show today are based on 3 key principles. So first of all, we use joint torque control, joint torque sensing and control in order to cope with the actuator dynamics and in order to make the highly geared drives back drivable. Secondly, we use passivity-based approaches for the whole body control. And third, we have a walking control algorithm based on the so-called divergent component of motion. And this divergent component of motion gives us a close connection.
Okay.
So that's live.
Motion and the
so this is the proof.
Yeah, that's the risk of a live demo.
Yeah.
Let's give it a second try.
Yes.
The point is maybe we switch at the same time to the quadruped. and give Christian the chance to restart the robot. A main point actually to come over to the quadruped is saying, you have seen we have torque control. As soon as communication stops or software fails, you realize that the robot is a rigid system. And maybe, Klaus, this is also bringing us to the second
yes.
type of system.
So I think what is interesting that the more robots behave like humans or animals, but still they are built from mechatronic components. And what do you think, in what areas we can expect bioengineering or biorobotics will come up with some disruptive solutions compared to our today's mechatronic robots? Do you have research in this area too?
Yes, maybe when you attended the talk, you remember this quadruped system. So all the systems we have shown so far are compliant by means of advanced control. We have a control loop at millisecond level measuring the joint torques and overcoming friction, motor inertia, and so on. Now, in biology, it's different because our muscles and tendons are compliant, and they are storing really mechanical energy. So this is what I'm trying to show you now, and we are trying to replicate in this system. And this is a rapid prototyping device, a quadruped, which is designed such that even if the motors are kept fixed, you have springs absorbing the energy. And you can see here, that's the intrinsic behavior of the system. And what we are trying to show now is that such a system with 12 degrees of freedom has several resonance modes, and we designed it in such a way that those resonance modes correspond to locomotion patterns. So maybe we can show now several locomotion patterns over here. And we start with walking. Walking is a type of locomotion in which we have 3 legs in contact with the ground. And then we go over to a second type of motion, which is trotting. And trotting is exciting another oscillation mode on which the frequency is much higher. You have 2 legs in the contact with the ground and 2 legs in the air at the same time. And then maybe we can go also to a third type of motion, which is called bounding. Actually, we cannot do galloping because we have do not have a spine over here, but we can jump with the system. And again, you excite the resonance motion. So I think this is an ongoing research because studying those nonlinear modes, as I mentioned in the introduction, it's a quite challenging aspect. Now we are back, hopefully. So I will, on the fly, hand over back to Christian and hopefully continue
Good luck.
with the humanoid
Good luck
demonstration.
to Toro. So I was informed that Toro had a foot surgery just yesterday, but he is now healthy again and should be able to walk.
And so what we want to show today actually is to walk over different terrain, and it should walk over the mat and over the stones. And especially the mat are quite a challenging environment because when it steps on this environment, it cannot statically balance. It has to adapt its contact forces all the time while looking over this surface. So there's no static balancing on this environment. So hopefully the robot should start walking now. Okay, now it approaches the mat. So this demo is fully autonomous. It utilizes some markers in the environment to find its way. No. But somehow, again, a bad luck happened because it was somehow touching the lower mat and was stumbling over it.
So perhaps Alin,
yes.
So we see here one of the humanoid robots, and people are most attracted by humanoids. Why? Because they are most similar to us, like you're walking Toro here. But what really makes a robot a humanoid? Is it the face, the hands, the legs, or is it there something more?
So maybe I can give a short answer, then handle over to Christian again. But I think for us, what's important is the functionality, much more than appearance, right? But of course, here we focus on leg locomotion because I think this is one of the really very, very challenging, still not completely solved aspects of humanoid robotics. Christian, maybe you can say something as well.
Yeah, I think humanoid robotics is used in many contexts, right? So some people who work on manipulation, they consider a mobile platform with 2 arms and hands as a humanoid system. In our case, we have focus on locomotion. So for us, the kinematic of the leg is important. So we have 6 degrees of freedom in the leg, and we can do arbitrary motions for the feet. And so far, we combine this with classic actuation principles. So we have the torque control and highly geared motors. And in that way, we implement walking algorithms. I think the next step would be to combine this with elastic actuators to have also more human-like actuation principles like muscle-like actuators. But this kind of environments, like we see it here, lab environments, or also this elastic mattress, is something which we can cope with also with the existing torque-based approaches. So now it's working. So as I said before, the robot cannot statically balance on the mattress while it's walking. And you see here a walking behavior where we adapted the footsteps a little bit because the robot is sinking into the mattress quite a lot. And it takes a bit smaller steps so that it can finish the whole stepping motions over the compliant environment. Okay, this was the first part of the demo. In the second part, you should see some walking motions with larger footsteps. So the robot is turning around, and then we will walk back with larger footsteps. And the footsteps have a size of about 40 centimeters. This is about 70% of the maximum footstep length we can achieve with this robot. And you see also some toe-off motion, which is necessary here in order to implement these large foot trajectories. And another important aspect is the walking algorithm based on the divergent component of motion. So here, the divergent component of motion is a concept which combines the center of mass position and center of mass velocity. So it's a composite variable, very similar to what we know from adaptive control. There also we have the sliding variables which combine position and velocity coordinates. And in terms of locomotion, this is very useful because this sliding variable allows us to separate the unstable and the stable part from the locomotion dynamics. And not only for the control, this is useful, but also for the planning, for the motion planning, because one can show that this DCM component only in linear trajectories from step to step. And this means that we can separate the dynamics and control from the motion, from the geometric motion planning. It's not full for the time-based trajectories, but the geometric planning can be separated.
So great to see that it is working and Toro is running and walking again. Great.
Sorry for the interruption.
Thank you.
This was live.
Thank you. This brings us to the end of our presentation. I hope you enjoyed the stay here in the lab.
Thank you, Arlene, for this exciting lab tour. Thanks to all your robot panelists, and thanks to your DLab team for this terrific show.
So bye-bye, and I hope you enjoyed the end of the conference.
Yeah. So, ladies and gentlemen, this closes now the 2 days plenary. Thanks for your attendance, and please stay with us for the grand closing ceremony following in this hall 1. See you there.